What we're looking at here is an ANOVA table for a linear regression, and we're going to cover two types of analyses. First, we're going to cover uncovering regression. And you may have already covered ANOVA at this point, or if you haven't covered ANOVA yet, you will be covering it soon. And the point I'm making in a really clumsy way here is that there's an ANOVA table for both a regression and what we call an ANOVA analysis. So in an ANOVA analysis, of course, you're comparing multiple groups. You're seeing if groups are different from each other, and they might have multiple levels. However, an ANOVA, of course, just stands for analysis of variance, and we can do that with regard to a regression too. So in our table, let's go through what we're looking at. We have a source of variation, and we write down what that source of variation is. Now, when we're looking at a regression like what we were just looking at, we have sources of variation related to the distance of individual points from the line itself. We have, and in fact, for each point, we could think of the total variation from the line as being a sum of the distance from the point to the line and the point to the overall mean, right? And we might think of how much variation is in the line itself. And so the first, what we call sums of squares, is we might sum up for each level of x. We might go through and say, okay, what's the estimated value of y at the regression line? And how far is it away from the mean, or y bar in this case? And let's square that, because that way we get rid of the problem with negatives canceling positives. So what that means in our slide here is that for each value of x, say x is 32, we're going to estimate the y sub I for that, which is different than the individual point. So there's also a y sub I up at 36 here, which is right along the line, which is different than the point itself, which in this case was right along the mean. So there's also a y sub I there. And for each of those, we're gonna calculate the y sub I from our regression equation. Okay. And then we're gonna take the overall mean, like here, right? And the mean is, of course, our dotted line here. So we'll take the estimated value of y at the line minus the mean and square it. And then we'll add those up for all values of x. And so all along the line, we go and calculate the values of y and look at the distance of those estimated values of y all the way to the mean. And we'd say, okay, how much variance is there in that line from the overall mean? Okay. And then we have some error, and what we're going to call error here in this case is the y sub i's, the actual values, so the black dots here, and the error is represented here by the solid red lines. It's the distance of those y sub i's to the y hat sub i's, and so the estimated value of y at each level of x. So in other words, just to make it say it a little bit more simply, what we're really looking for here is we're looking for the distance from the actual values that we've seen in our data set from the estimated values on the line. And so the equation values versus the real values. So we're seeing how far away each point is from its estimated value, and then we're squaring it because sometimes it's below and sometimes it's above that line of best fit. Now we already knew that the very first one that we covered here, the sums of squares regression, the y hat sub I minus y bar, that tells us something about how far away our regression is from our overall mean line. The error term here will look familiar to you from what we just talked about, because these are the squares that we were trying to minimize when we had the line of best fit. We were minimizing the distance of the individual points to that line. And that's exactly what our error term is. So if our line of best fit is good, that error term is really small because we've minimized it by getting the line of best fit through those points. Then the total error should look familiar to you. In fact, that total error looks something like our variance equation, which is where we started. Each of these levels has a degrees of freedom associated with it, and we'll talk about that in just a second. And then we can talk about it having a mean squares where we can divide by those degrees of freedom to get the average variance due to each source of variation. Sometimes these are calculated a little bit differently, and you'll often generically see ANOVA tables for regression represented like this. And the next thing we want to talk about is what the F ratio is, and that's how we're going to use the values we just calculated to come up with a score that we can then test for significance to see if we get the line that we got due to chance alone.